Legacy embedded systems minus supervisory control and data acquisition, SCADA. Let us explore the high-stakes world of SCADA, which stands for Supervisory Control and Data Acquisition. In the world of IT, we are usually worried about protecting data and websites, but in the world of operational technology, or OT, we are protecting the physical world. SCADA systems are the massive, distributed brains that control our most critical infrastructure, including power grids, water treatment plants, and automated manufacturing lines. To understand SCADA, you must look at how it bridges the gap between digital commands and physical movement, and why its reliance on legacy and embedded systems makes it a primary target for high-level cyberattacks. The architecture of industrial control. A SCADA system is not a single machine, but a complex hierarchy of components working together. At the top is the Master Terminal Unit, or MTU. This is the central command center, where human operators monitor the entire system on a screen. In the middle are the Remote Terminal Units, or RTS, and Programmable Logic Controllers, or PLCs. These are small, ruggedized computers located out in the field, at a substation, or on a factory floor. They receive digital commands from the MTU and translate them into physical actions, like opening a water valve or slowing down a conveyor belt. At the bottom are the sensors and actuators. These are the nervous system of the plant. Sensors measure things like temperature, pressure, and flow, while actuators are the motors and switches that perform the actual work. The challenge of legacy and embedded systems. The biggest risk in SCADA environments is the presence of legacy systems. In a standard office, a computer is considered old after 5 years. In an industrial plant, a PLC or a control server might stay in service for 20 or 30 years. Many of these machines run on ancient operating systems, like Windows XP or even older proprietary code, that have not received a security update in over a decade. They were designed in an era before the internet was a threat, so they often lack basic security features like encryption or password protection. Furthermore, these are embedded systems. This means the software is baked into the hardware. You cannot simply install an antivirus program on a water pump controller. This makes these systems incredibly difficult to patch and defend against modern hacking techniques. The myth of the air gap. For a long time, SCADA security relied on the air gap. This is the idea that because the industrial network is not physically connected to the public internet, it is safe from hackers. However, history has proven that the air gap is a myth. Attacks like Stuxnet showed that a hacker can jump over an air gap using something as simple as a poisoned USB drive. Once a piece of malware is inside the SCADA network, it can travel through the insecure legacy protocols, like Modbus, and take control of the physical hardware, potentially causing catastrophic physical damage to the plant. Security and monitoring. From a cybersecurity perspective, defending a SCADA system requires specialized tools. Because you cannot install software on the embedded controllers, you must monitor the network traffic from the outside. Security professionals use industrial intrusion detection systems to watch for unusual patterns. For example, if a water valve that usually only opens once a day suddenly starts opening and closing 10 times a second, the system can flag it as a potential attack. As we discussed with syslog, maintaining accurate, synchronized logs from these legacy systems is critical for understanding what happened during a failure or a breach. By mastering the balance between ancient legacy hardware and modern security monitoring, you will be prepared to protect the physical systems that keep our modern world running.